One blast could erase Earth's ozone in minutes from thousands of light years. That blast is a hypernova, a star collapsing and firing lethal jets. Here's the immediate takeaway: hypernovas are rare, directional, unbelievably energetic. They can outshine entire galaxies for a few frantic seconds. They are the loudest deaths of the biggest stars we know. Today we will open that blast and see its engine. We will meet the jets, the black hole, and the fallout. And we will ask the only scary question that matters. Could one aim at us, and how would that end? Breathe once, because the numbers you are about to hear terrify. But the universe also gives us warnings and escape angles. Let's step inside the brightest explosion nature has ever built. A swollen blue giant floats over a dusty cradle, quietly burning. A hypernova is an extreme supernova from a very massive star. You should care because it can beam deadly radiation across vast space. The star grows an iron core, which gravity crushes past breaking. The core collapses into a black hole or an ultra-magnetized neutron star. Matter falls inward, heats to billions of degrees, and forms a disk. Magnetic fields whip the disk and squeeze twin jets to near light speed. Those jets punch through the star and dump energy into space. The outer layers explode outward at tens of thousands of kilometers per second. The light show spans gamma rays, X-rays, and a blinding optical flare. In real terms, kinetic energy reaches about 10 to the 45 joules. That is more than our sun will radiate in its entire lifetime. One famous flavor links to stripped, broad-line type Ike supernovae. Their spectra show iron and oxygen, moving at 30,000 kilometers per second. Another flavor involves pair-instability, where the star completely tears itself apart. In both cases, the heat, the speed, and the beam are the threat. Rule of thumb: the narrower the jet, the farther its danger reaches. So the picture is simple: a giant star dies and fires a lance. Gas falls inward, heats up, and spins into a furious disk. A collapsar is a collapsing core that feeds a newborn black hole. It matters because the disk is the engine room of the jets. The disk gulps a sun's worth of matter in tens of seconds. Temperatures soar, while neutrinos stream out in astounding numbers. Magnetic fields thread the disk and latch onto the newborn hole. They twist like cables and extract rotational energy, fast and violent. That energy drives twin jets, which accelerate to Lorentz factors over 100. The jets are narrow, just a few degrees across at launch. They shove aside stellar layers, carving a tunnel to freedom. As the tunnel opens, shock waves heat the outer envelope. Radioactive nickel forms, which later powers the bright optical supernova glow. Think of a fire hose, except it sprays plasma near light speed. Now swap the hose for a jet and the yard for space. Observers then see a gamma ray burst, followed by a fading afterglow. The afterglow slides from X-ray to radio over days to months. For numbers, jet energy can top about 10 to the 44 joules. The isotropic equivalent can seem higher because the beam is tight. Net result: the disk and fields turn gravity into a focused storm. Far beyond the star, a pencil-thin beam rips through interstellar clouds. A gamma ray burst is the bright, high-energy flash from those jets. You should care because that flash can hammer atmospheres from afar. The beam is tight, often only a few degrees across. That focus makes the apparent energy look absurdly high. The light arrives as millisecond spikes, stacked into tens of seconds. High-energy photons scatter off dust, making expanding rings across the sky. The flash is followed by an afterglow that fades as a power law. Polarization can be strong, which hints at ordered magnetic fields. If you are off-axis, you see a faint, slower rise. If you are on axis, you get the punch straight on. For scale, a typical long burst lasts about 30 seconds. The brightest events can reach about 10 to the 46 joules. Even then, danger drops fast with distance and beam angle. Bottom line, the beam is narrow, fast, and brutally efficient. An ancient star cluster sits silent while a titan reaches its end. A pair-instability supernova happens when gamma rays create electron-positron pairs. That robs pressure, the core falls inward, and ignites explosive oxygen. The blast unbinds the star, so nothing compact survives the chaos. It matters because the energy rivals collapsars, yet there is no jet. The process runs hot and releases enormous nuclear burning. The shock tears outward and hurls shells at blistering speeds. Nickel yields can be huge, so the optical light can linger. Some events glow for months, with broad peaks and heavy elements. For numbers, energies can hit about 10 to the 45 joules. The debris expands in nested shells that collide and brighten again. Astronomers then map chemical layers, using spectra like fingerprints of depth. Quick comparison: collapsar's beam, pair-instability blasts everywhere at once. Bottom line: different engines, same terrifying scale of power. A live feed of detectors lights up, while telescopes swing in unison. In 2022, one burst rewrote records and headlines across the world. GRB 22109A was called the boat by many. That nickname means the brightest of all time for gamma bursts. It lasted for minutes with hard spikes and a stunning afterglow. X-rays scattered off dust, forming huge rings that grew for days. Observatories across Earth saw the rings, expanding like ripples in night. The optical afterglow was so bright, backyard scopes could track it. Energy numbers were extreme, even after correcting for distance and beaming. The jet likely had a very narrow core, with huge Lorentz factors. Fermi and Swift caught the first flash, and guided ground follow up. Radio dishes watched the shock plow outward into the surrounding medium. One estimate placed the apparent energy near 10 to the 47 joules. That is the isotropic equivalent, not the true beamed energy budget. Still, the event showed what a pointed lance can actually do. So the lesson is, boat was a wake-up siren, not a fluke. Now stand on a nearby planet as the beam arrives overhead. The sky turns electric blue while air chemistry starts to scramble. Gamma rays split nitrogen molecules and flood the air with radicals. Ozone breaks apart and ultraviolet sunlight reaches the ground unhindered. It matters because surface life depends on that thin, fragile sunscreen. Models show large ozone losses within weeks after a close burst. Nitrates rain out, acidifying water and stressing the food web. Blue light scatters hard, so strange halos linger for days. How close is dangerous depends on the beam and event energy. A rough threshold is 2,000 light-years for truly severe damage. Smaller hits could still disturb climate and spike mutation rates. Recovery is slow over years as chemistry climbs back to balance. In one scenario, a burst at 1 kiloparsec could strip half the ozone. That pushes UV exposure to levels that many species cannot endure. Rule of thumb: danger drops with the square of distance. Net result: risk exists, but the odds and geometry favor us. A network map glows across Earth, linking space and ground observatories. Finding hypernovas starts with a trigger from space gamma monitors. It matters because seconds count before the afterglow begins to fade. Swift slews fast, pins a location, and opens the X-ray eye. Robotic scopes race to catch the optical flash and measure color. Spectra reveal broad lines, missing hydrogen and high-velocity metals. Redshift gives distance, turning brightness into actual energy numbers. Polarization gauges magnetic order, while radio maps the blast wave. X-ray rings measure dust, which refines distances along the sightline. Data then flows to brokers, which alert teams within minutes. Analysts fit afterglow curves and estimate jet opening angles. Beaming correction shrinks energy by factors of 100 or more. For reference, long bursts last tens of seconds at cosmological distances. In galaxies like ours, hypernova-style events are probably rare, maybe once in a million years per galaxy on rough average. What to remember: coordinated eyes turn chaos into understandable numbers. Look back at the star fields and the scars they leave behind. Hypernovas seed space with iron, nickel, and oxygen for new worlds. They also clear gas and can quench or trigger nearby star birth. Over time, they help set the tempo of galactic ecosystems. For us, the fear is balanced by geometry and vast distances. Space is big and the beam is small, so odds stay low. We also watch the sky and would see a threat early. Telescopes and models improve yearly, alerts move faster and maps sharpen. If one ever aimed our way, shelter would be possible. Deep time reminds us that life adapts and finds new paths. Remember the opening line: a single blast can sterilize from afar. The flip side is richer elements and stories written in starlight. If this felt vast and terrifying, it still belongs to us. Share this with one curious friend so the wonder keeps spreading. That opening claim was real: a single beam could strip ozone. But the takeaway is steady: geometry and distance keep us safe. We can respect the power without living in fear every night. If this sparked wonder, pass it to a friend who loves space. One share grows the watchful network and invites better questions. I will keep the sky on your radar with clear numbers and scenes. Until the next bright echo, keep looking up and breathe easy.